So in this video we're going to go over how to show that a function y equals f of x is a solution to a differential equation. And the idea is that if y equals f of x is a solution to the differential equation over some appropriate interval, if you plug y, the thing that you're claiming is the solution, and its appropriate derivatives into the differential equation, you should generate an identity. So if we're saying that this side equals 0, when we plug in what we think is a solution and its appropriate derivatives, in this case a second derivative, we should get the identity 0 equals 0 when we're done, or we should be able to demonstrate that when we plug in y and y prime into the left hand side, that we can simplify that to 0, which is what the claim is, that if we have a solution and plug it and its second derivative in, will generate a 0. So we should be able to demonstrate that. So here's the idea. I'm going to take my differential equation, which is y double prime plus 25y, and we're trying to verify that this y equals c sub 1, where c sub 1 is just some real number, some constant, times the cosine of 5x. We want to verify that this is a solution for this differential equation. And the idea is, if it is a solution, we should be able to replace the y with c sub 1 cosine of 5x, and we should be able to replace y double prime with the second derivative of this, and when we simplify, we should wind up with the 0 when we're done. So over here, for my scratch work off on the side, I'm going to write down my c sub 1 cosine of 5x, and I know that I need the second derivative of y. So first I calculate the first derivative, which is going to be negative 5c sub 1 times the sine of 5x. Again, we take the derivative of cosine of 5x, which is negative sine of 5x, and then the chain rule says that we need to take the derivative of the inside, which is a 5, so we'll get this. And then we take the second derivative, y double prime. So the chain rule, we're going to have the derivative of a 5x is 5, so we're going to get a negative 25 c sub 1, and the derivative of sine is cosine of 5x. So here's the first and second derivative of the proposed solution. So now we step over here and we replace y double prime with this. Y double prime is negative 25 c sub 1 cosine of 5x plus, we have 25 times y, so replace y with c sub 1 cosine of 5x, c sub 1 cosine of 5x. And if this is a solution, this should evaluate to 0, which it does. Negative 25 c sub 1 cosine of 5x plus 25 c sub 1 cosine of 5x equals 0. And we know that if we plug in a solution, we should generate a 0 based on the original differential equation. So that verifies that this is indeed a solution to this differential equation. Now, solutions may be implicitly defined. So it says show that this is an implicitly defined solution for this differential equation. And remember, when we have an implicit formula or equation, I should say, what we're identifying is that it's not been solved for y, and in fact it might not be solvable for y, but y is in here implicitly. So I don't have a y equals, it's not explicitly defined, but it is implicitly defined. So I'm going to start by writing down the left hand side of this differential equation. It's 2xy plus, and I have x squared plus 2y times dy dx is the same as y prime. And then I'm going to go ahead and find the derivative y prime and replace y prime with the derivative. And then I'm going to see if that simplifies. When I do it, I'm going to see if it simplifies to a 0, so equals. And my solution, if it is one, is implicitly defined. It's not been solved for y, so I get x squared y plus y squared equals c. And then what we need to do is implicitly differentiate both sides. So the derivative of c is going to be 0. The derivative of x squared y, will need to use the product rule, so it'll be 2x, the derivative of the first term, times the second term, plus the first term x squared times the derivative of y, which is just y prime, plus, and now I have a chain rule, take the derivative of y squared, which is 2y, times, now by the chain we'll take the derivative of y, which is just y prime, and that equals 0. And now we want to solve this for y prime so we can make the substitution up here. So I'm going to subtract the 2xy from both sides, and then on these two terms, which each have y prime, we'll factor that y prime out. Factoring y prime off this first term leaves an x squared. Factoring y prime off of this term leaves a plus 2y. And then solving for the derivative y prime, we get negative 2xy all over. My face is somewhere in here blocking things, over x squared plus 2 times y. And so we'll step up here, and I won't worry about trying to solve this for y. So I'll just take my 2xy right here, plus x squared plus twice y times y prime, but replace y prime with this right here. So replace y prime with the negative 2xy over the x squared plus 2y. And then simplify, I'm going to get 2xy here. Here I get x squared plus 2y divided by x squared plus 2y equals 1. And 1 times negative 2xy is just a minus 2xy. So this simplifies to 1 as long as this expression in the denominator isn't equal to 0. And then we get 2xy minus 2xy is 0, which, if this implicitly defined function is a solution, when I plug in its derivative, I should get it to evaluate to 0, which it did. So that verifies that the implicitly defined solution was in fact a solution.